Hi, Subra.
Hello. So should I start? Okay.
Hello everyone. We have Shubhrajit Bhattacharya, final year BSc student at CMI, to present his talk on Galois theory of local fields. Over to you, Subra. Start.
Okay. Thank you. So I will first start with an overview of why these fields are called local. So this classification, local and global, has actually number theoretic significance of fields. So in number theory, we study these two kinds of fields, and global fields are like the field of rational numbers or the field of functions with coefficients in a finite field. So they are called global fields. And the nomenclature local came from 1930 articles on local class field theory. So which were written in German and French, and they used to call it local. So so this German term actually they tried to mean small, but when it was translated to English, it became just local. So they meant actually class field theory in the small, but it was translated into English like in English just local class field theory. And since then, this nomenclature local class field theory prevailed, and hence we didn't change this nomenclature, and we call this local fields. But there are also some other reasons why we should call these fields local. These local fields actually look like the ring of germs of functions near a point on a variety. So, and also the ring of integers of a local field is a local ring. That means those rings have only one unique maximal ideal. So these can be two reasons why this local name has not been changed to small. And the relation between local and global fields. So one of the most fundamental theorem in
So
number
can we
theory.
say that local fields are the field of fraction of local rings or something like?
Yeah. So you know
Exactly.
that yeah. So you know that local ring of functions, the
Mm-hmm.
concept of local ring of
Mm-hmm.
functions. So those rings are local rings, like they have only one maximal ideal, and
Mm-hmm.
they are defined by the valuation near that point.
Mm-hmm.
And so these the ring of integers or the valuation ring of these fields are local rings, and that's what one reason uh, that we should call these fields local. And here is the local global principle. The most fundamental theorem is that Hasse-Minkowski's theorem, which says that quadratic form has the solutions in Q if and only if it has solutions in all local fields Q sub P. So we will see what is exactly Q sub P. And when P equals to infinity, we say that this QP is actually R when P equals to infinity. So this is the Hasse-Minkowski principle. And but this is not in general true for higher genus curves. So for genus 1 curve, it is conjectured that the failure of Hasse-Minkowski theorem is finite, in the sense that the Tate-Safarovich group. So this is not related, but I'm just saying. So the Tate-Safarovich group of an elliptic curve over Q, which actually measures the failure of this Hasse-Minkowski principle for an elliptic curve, which is of genus 1, and quadratic forms are of genus 0 curve. So, and it is conjectured that this Tate-Safarovich group is finite. That means the failure of Hasse-Minkowski principle is not as large as infinity. So here is one motivation behind studying local fields. So uh, we see that in every mathematical breakthrough or every great mathematical theorem actually studies some deep relations between different mathematical objects rather than just studying a mathematical object independently or its internal structures, etc. So what we do exactly is we just try to find how one set of mathematical objects interact with some different set of mathematical objects. So that's why we study the representations of a Galois group of these rational numbers. So this is called the absolute Galois group of Q. So this is very easy to see that studying number fields is equivalent to studying this absolute Galois group, because all the number fields, that is all finite extensions of Q, are contained inside this tower. So whenever we are trying to study some arithmetic over a number field K, so that information is contained inside this absolute Galois group, where Q bar is a fixed algebraic closure. And in general, for any number field K, we are interested in this absolute Galois group of K, which is a Galois group of K bar over K, where K bar is a fixed algebraic closure of K. So, but here we don't study the internal structure of this Galois group. In fact, we cannot study in the internal structure of this Galois group. So that's why we study representations of these Galois groups, and they are known as Galois representations. So we will see in details what our Galois representations are and what different classes of Galois representations we like to study. So, and rather than studying the Galois representations of that whole absolute Galois group of Q, it is easier to study these subgroups. So this is the field of periodic numbers. And if I take this Galois group, absolute Galois group of this field of periodic numbers, it turns out that it is a subgroup of these absolute Galois group of Q. And these Galois groups are easy to study in the sense that their Galois representations are easy to study, and the category of their Galois representations are easy to
How
study.
you define the decomposition group?
Yeah, so the decomposition group, my pen is not working.
Okay, but
So the
already you can tell me.
decomposition group is just the set of elements inside this Galois group which fix the prime ideal, or which fix the prime with respect to which it is completed. Here the prime means the absolute value. So the decomposition group contains the elements inside this Galois group which fix the absolute value, periodic absolute value.
But that prime would be living in the general global field, right?
Yeah, yeah. So for for a finite extension, the decomposition group at a prime ideal is the set of those elements inside this that Galois group of L over K, which fix the prime ideal. That is, sigma of that prime ideal is equal to the prime ideal itself.
Okay.
So for defining the decomposition group of an infinite Galois group, so this is an infinite Galois group. So we can also define that to be the inverse limit of all decomposition groups of the finite sub-extensions.
Okay, so by inverse limit, you define this particular GQP.
That is the most that is the most efficient way, because we cannot say that a prime ideal of QP extends to a prime ideal of QP bar, because it does not actually.
Okay.
The absolute value extends to the algebraic closure, but the prime ideal does not extend to a prime ideal of that. So that is a problem. So here are two different cases. So sometimes we study the Galois representations of GQP, uh, which is a group homomorphism from GQP to, sorry, this should be GLV. I made a mistake here. My pen is not working. Sorry.
GLP?
Sorry, that should be GLV.
Okay, yeah. So
I missed it, sorry. That should be a representation is a homomorphism from GQP to GLV.
what
The
would
set of
happen
our
if P
linear-
would be equal to L?
Sorry, my pen is not working. Just give me a minute. I'm just trying to stop share and reshare again. Yeah. My pen is not working. Just give me a minute. If my pen doesn't work, I can't explain some things I haven't written. So
It's
I'll-
okay. Means you go ahead. Means you cannot
Yeah.
depend upon this technical glitch.
Okay.
Share the slides again. It was not visible now.
Yeah. I have stopped sharing. I will reshare again. Sorry. Let us wait a minute. And now it seems that it will work. Okay. Yeah, now it's working. Thank God. Yeah, can you see the screen now?
It is coming here now. Come visible.
Yeah, so this should be GLV, I want to say.
Yeah. So I was asking if P is equal to L, then what would happen?
Yeah, so when P is L, then the situation is complicated and it is known as periodic Hodge theory.
I see.
This is a separate subdiscipline of number theory which studies periodic representation of GQP. So for this thing, there is a book of which studies only elliptic representations. So the name is like a elliptic curves and elliptic representations. Maybe I don't remember quite correctly, but and the periodic for the periodic representations, there are some sophisticated constructions by Fontaine, etc. So and that is a completely different subdiscipline known as periodic Hodge theory. Yeah.
What resemblance it had with Hodge theory? Any idea?
Sorry.
What resemblance it has with Hodge theory, usual Hodge theory?
Yeah. So
I cannot relate basically.
Yeah. So in real Hodge theory, there is the main theorem is the Hodge decomposition, right? Yeah, so the Hodge decomposition, and in periodic Hodge theory, Fontaine constructed a ring known as BDR. It is known as the Deram ring, which contains periodic analogues of periods. Periods like one example of a period is this thing. So if I integrate 1 over z dz around the unit circle over the complex plane, then I will get 2 pi I, right? So this is an example of a period. The period comes out of integrating some cycle with respect to some differential form.
Yeah.
So there was a need to construct a periodic analog of such periods to get periodic Hodge decomposition, which is in the complex
see.
Hodge theory that you were saying.
Okay.
So this ring has an element sometimes denoted as T, which which allows us to prove same decomposition theorem as there is in complex Hodge theory.
What is T?
In complex Hodge theory, there is a Hodge decomposition.
No, this T you were mentioning.
Yeah, so T is the periodic analog of say 2 pi I.
Okay.
Yeah, so
Okay.
maybe I can tell more about this in my Galois representation slides.
Okay, maybe you can tell, but yeah, if not needed, don't worry. Go ahead.
Yeah. So these are very
Advanced thing.
complicated constructions. Yeah. Yes, I have given a reference for this periodic Hodge theory. Yeah, so there are more motivation for studying local fields. So there is a society of periodics, and they have.
Can you zoom the second T cell?
Yeah.
What is
So
written there?
they have
Bus.
enlisted 7 reasons
Top P
why
region,
we
why
should
keeping better than great.
Yeah. So you don't need a negative sign. That is.
You have this T cell?
No. Yeah, so maybe one should try to add many more such reasons for p equals to 11 or p equals to 30.
Okay, great.
Yeah, Kiran Kedla wears this t-shirt in many lectures. You can see in YouTube. You can find this in this link. Now we move to the definition of local field. So local fields are so the main theorem. One main theorem of this slides are to show that the local fields are isomorphic to either R or C or QP for some prime, or FQ double round bracket T. This means the ring of this means you have the ring of power series in T, and then you take the field of fractions of it.
Miss FQT, you were saying that what is ring of power series? Okay, so what is Q? What is Q?
Where Q is any prime power. FQ is the finite field.
Okay, so these Laura series are defined over finite field?
Yeah, finite. Okay. FQ is a finite field. So this is a standard notation for finite field, right?
Yeah.
Finite field filled with Q elements where Q is a prime power. Yeah. So local fields are exactly isomorphic to these things, or finite extension of this, or QP. So before that, we need to define what is a local field. So we are not giving algebraic definition. We will give a topological definition. Topological characterization is the most standard way to study local fields. So a topological field is any field with topology defined on it, such that the multiplication operation, the inverse taking inverse and the x, and multiplication, addition, and taking inverse, all these operations are continuous maps. And a topological space is called locally compact if each point has a compact neighborhood inside that topological space. So, and what is an absolute value on a field? So an absolute value on a field is a map from K to the non-negative reals, which satisfy these formulas, that conditions that norm. So you can say this a norm. So norm of x is 0 if and only if x equals 0. It is it preserves the product, and also it satisfies the triangle inequality. So from here, you can definitely check that this map is a metric on K, right? Because it satisfies the triangle inequality. So it defines a metric on K. And we say that K is non-Archimedean if this absolute value satisfies the stronger triangle inequality, which is also known as sometimes ultrametric inequality. Mod of x plus y less than equal to maximum of mod x comma mod y for all xy inside K. If that's not true, then we say that K is Archimedean. So an example of an Archimedean field is R. And now we come to the definition of a discrete valuation. So a discrete valuation in a field K is a map free from K star. K star means the multiplicative group of K star from Z that satisfy the following properties. That V of xy is V of x plus y for all xy inside K star. And V of x plus y is greater than equal to minimum of Vx and Vy. And we can extend this definition to all of K by defining that V of 0 equals infinity and V of x equals infinity if and only if x equals 0. So these definitions are clear, right?
Yeah, what are the examples of discrete evaluations?
Yeah, so I will just sketch in the next slide. So a local field is so this is the topological characterization of a local field. So a local field is a field K together with an absolute value on it. And this you want to take this absolute value to be non-trivial. So non-trivial absolute value on K that such that the topology it induces, that means the metric with respect to this norm and the topology with respect to that metric. So with respect to that topology, K is a locally compact topological space. So they are called local fields. So now, given a discrete valuation V on K, we can define an absolute value with respect to that discrete valuation by this formula. That x sub V defined to equal C to the power V of x, where C is some number between 0 and 1. So using these two conditions, you can easily show that this formula satisfies these properties. So given a discrete valuation, we can get a absolute value on a field. So now we give the most fundamental example of a discrete valuation. So by the fundamental theorem of arithmetic, you know that every integer in which is not 0, there exists a unique natural number Vpn, natural number or 0. So Vpn such that p to the power Vp of n fully divides in. Divides in, this is the standard notation. That means that Vp of p to the Vp of n divides in, and p to the Vp of n plus 1 does not divide. That means Vp of n is the maximal power of p that divides in. This is true, right? By the fundamental theorem of arithmetic.
Mm-hmm.
And now this defines a valuation on Q, which we can extend from Z star to Q by this formula. We declare that Vp of m by n for a rational number m by n to be Vp of m minus Vp of n, and Vp of 0 we define to be infinity. So you can easily check that this defines a discrete valuation on Q, and then we can get a absolute value which is defined by mod xp is defined to equal p to the minus Vp of x. So here we are taking C to be 1 by p. So we could have taken any C inside 0 comma 1, but we are taking p. So there is a reason for taking 1 by p. So I will just make it clear. So do I need to recall the concept of two absolute values being two absolute values being equivalent when they are equivalent? Yeah, so two absolute values, say this absolute value 1 and absolute value 2 are equivalent when uh, there is some positive real number t such that this absolute value 1 is equal to this absolute value to the power t. And this is the classical theorem of Ostravsky, which says that if we have a non-trivial absolute value on Q, then it has to be either the usual absolute value on reals, or it is equivalent to some periodic absolute value defined defined above for some prime p. So you can find the proof in Neil Koblitz's book on periodic numbers. There is a proof, and here we explain why we chose C to be p to the p to the minus 1. So the reason behind this choice is to get a nice product formula.
There is some question there.
Yeah, what is the question?
Due to non-equivalent absolute values.
Induce different topologies. Yeah. Yeah, so that's what I'm here trying to say, right? So if you take a different prime and you take this, you take a different absolute value, then they will define two different topologies on Q. And there are many equivalent definitions. So, I see. You are trying to say that the definition of two absolute values being equivalent are when they induce same topology, right? I see. Okay, but there are many definitions. So there are one other definition that that one would like to say that two absolute values are equivalent if there are two constants C1 and C2, such that mod of this thing as a function is less than equal to C2 times this 2 and say C1 times C2. So these are all equivalent definitions. Yeah. What you are saying, they are all equivalent conditions for two absolute values being equivalent. So we are here giving the definition as powers because we are in a field and we can multiply things. So this multiplicative definition will be more useful. And here the reason behind the choice C equals to 1 by P is to get a nice product formula. So for all x inside Q, we have this product formula where mod x is the usual absolute value. And here we take the product over all primes and the absolute value, and the choice of this p to the minus 1 gives us this product formula. And actually these product formulas are used to characterize global fields. So we will not go into that, but there are generalizations of this product formula for all finite extensions of Q, for example. So how do we generalize this p-adic valuation to a script p-adic valuation for a finite extension of Q? So let K be a finite extension of Q. And so then this is a fact from algebraic number theory that every fractional ideal of K factors into prime ideals uniquely, right?
Yes.
So that is a fundamental property of a Dedekind domain. So then again, just as we did for the fundamental theorem of arithmetic. So if I take the script IOK to be the group of all fractional ideals of K, so then there is a unique for each if for each ideal inside this IOK, there is a unique natural number, or there is a unique integer, say, such that VP of that ideal occurs. So that is P to the power VP of A occurs in the prime factorization of that ideal. So we get a map from this IOK to Z. So now we use this thing to define script periodic absolute value on K, which is defined as U to the power minus VP of XOK. Here XOK is the principal fractional ideal generated by the element X. And VP is the power of P inside power of P in the prime factorization of that ideal. And Q is the cardinality of the residue field extension. So this is another fact from commutative algebra or algebraic number theory, whatever you want to say, that this OK mod P is a finite field. And
Yes.
hence it is a power of P, and we take this and Q to the power minus. So again, we could have chosen any C inside 0,1, but we have chosen this number because we want to get a nice product formula like this. So for Q, this product formula is very easy to prove, and so you can just simply see that why is it true. But for an arbitrary number field, this product formula will take some work, and these are called the normalized absolute value. And in fact, if we take any C inside 0,1, then we will see that that the corresponding absolute value will be equivalent to this absolute value. So we kind of presenting that equivalence class of absolute values by this particular absolute value, and this is known as the normalized absolute value. Now we define these important notations. So for a local field K with an absolute value, say absolute value which is induced by some discrete valuation V on K, then its ring of integers coincides with its valuation ring. So this is the definition of valuation ring of K, which is same as X inside K such that V of X is greater than or equal to 0. So this also coincides with the ring of integers of K. This is the group, multiplicative group of the ring of integers, which are exactly those elements with absolute value 1. And this is the unique maximal ideal. So for, as I have said in the beginning, that the ring of integers of a local field is a local ring, and it has a unique maximal ideal, and that maximal ideal is exactly this, containing elements with absolute value less than 1 or discrete valuation strictly greater than 0.
This residue field is also finite field?
Yeah. So in our case, a local field is defined in this way, that the residue field has to be finite. There are notions of higher local fields, higher dimensional local fields. So in that case, the residue field can be of infinite dimension. So what we are studying, these are known as one-dimensional local fields. There are some recent developments on higher dimensional local fields. So higher dimensional local fields are like we say that K is an n-dimensional local field if its residue field is an n-1 dimensional local field.
I
So
see.
zero-dimensional local fields are finite fields, and that's why it is one-dimensional local field. Because its finite field, its residue field is finite. So
So is there any significant difference between the ring of integers of local and global field, or they are basically algebraic properties are all same?
not algebraic properties are all same, because for a global field, okay, if K is a global field, that is, if it is a finite extension of Q, then it may not be local
PID.
ring, right?
Mm-hmm.
Because it has infinitely many primes.
Mm-hmm.
K will have infinitely many prime ideals because for each prime inside Q, there will be one prime ideal which lie above P, and there are infinitely many prime ideals, so there will be infinitely many prime ideals inside OK. And as we know that in Dedekind domains, non-zero prime ideals are maximal, so OK will contain infinitely many maximal ideals. But here in the case of a local field, there are only one maximal ideal. So that's a crucial difference between local and global fields. And that's what makes the study of local fields easier than global fields. Because if you take say, if you take any local field K and let A be the ring of integers of that, and if L is a finite extension of that, and then take B to be the ring of integers of L, then if you take the principal, if you take the principal ideal, sorry, so if P is the unique maximal ideal of A, then BP will be some Q times some E, where Q is the unique maximal ideal of P. So here the ramification and etc. will be easier to study. We'll see later. We'll see in the following slides. And any generator of this unique maximal ideal will be known as a uniformizer of K, and denoted sometimes at pi K. Okay, so this notation is clear, right? Yeah. So now we define what is QP. So QP is nothing but the completion, topological completion of Q with respect to a periodic valuation. So I assume that all of you know what is a topological completion. So we can complete a topological space with respect to a metric space with respect to its metric by using Cauchy sequences, right? And QP is nothing but the completion of Q with respect to this periodic valuation. So when P equals to infinity, then this periodic valuation is the usual absolute value, and we know that we get R by completing Q with respect to that usual absolute value, right? So that shows that R is a local field also.
Conversing periodically just mean that it is converging under this special value norm and something else or something else.
Yeah, periodically means that that it is converging with respect to this norm.
Particular and nothing else. Nothing more.
No.
Okay.
No. Yeah. So in case someone confuses, I just wrote it. Because the elements of QP, they can also be treated as elements of R. So there is
two different.
There is an injection QP inside C. So elements of QP can also be seen as elements of C. So the absolute values should not be confused. So when we talk about QP, we are always talking about the absolute value P, periodic absolute value. So we define the periodic absolute value of a general element inside QP. So we know that we know what is the periodic absolute value for an element inside Q, right? but we don't know what it will be for QP. So we just define it as the limit of any Cauchy sequence that converges to X. So it is an easy exercise to show that if you take a different Cauchy sequence, then that will also converge to the same limit, etc. So that's just a routine check. So by a global field, as I said before, by a global field, we mean finite extensions of Q or FQT. This is now the field of rational functions with coefficients inside Q. So this finite extensions of Q are known as number fields, and finite extensions of this field are known as function fields. So some of you might have known that almost all the arithmetic we do for number fields have generalization for function fields, right?
What?
Yeah, so the arithmetic we do for number fields, K over Q. So most of the theorems have generalizations or analogous theorems for finite extensions of FQT for function fields. So in fact, some theorems for function fields are known, but not known for number fields.
Life is easier there.
Yeah. And now we just state some facts without proof. So you can see these two references I've listed for the proof. So the first fact is if K is a local field and the absolute value on K is this, then K is a, sorry, this should not be local. So if K is any field, so don't assume local. If K is any field and suppose that there is an absolute value on K, then K is local if and only if every closed ball in K is compact. And then if K is a local field with the absolute value this, then K is complete. That is, K is topologically complete with respect to the topology induced by this absolute value.
Whatever absolute value.
Yeah. So when we have defined the local field, so we have said that a local field is a field with an absolute value on it, such that with respect to that absolute value, it is locally compact. So this absolute value is that in the definition. So when we say that K is a local field, it automatically comes with an absolute value by definition.
So there is no need to say even that key with an absolute value, because in local field we need that assumption.
Yeah.
So every local field is a complete always.
Yeah. So this is a theorem.
By definition, maybe using something.
No. By definition, it is locally compact, but not necessarily complete. You have to show that this by definition it implies that K is complete.
Okay.
Yeah. By definition, K is a local field when we have an absolute value on K, and the topology with respect to this absolute value is locally compact. That means every point inside K has a compact neighborhood. And the third fact is if K is a field with absolute value induced by a discrete valuation V on K. So just as we have seen, so you can suppose K to be Q. Here you can suppose for example, this is the periodic absolute value, which is induced by the periodic discrete valuation. So then let A be the valuation ring. So here for the periodic absolute value, the valuation ring will be ZP. Yeah, so you can guess what is this, right? This is the localization of the integers at the prime ideal P. This is not ZP. They are two different things. This is the periodic integers, but this is the localization of Z at the prime ideal P.
Mm.
So then, and let P pi be a uniformizer. In this case, an uniformizer will be P. And then K is a local field if and only if K is complete and the residue field A modulo pi A is finite.
Okay.
Yeah. So in that case, you can easily say that GP modulo ZP is isomorphic to FP, which is finite. So I have just given you an example why this is true. The proof is almost the same as you prove this particular example. And the fourth fact is if L is let L be a global field, that is a finite extension of Q or either a function field FQT. And let we have an absolute value on L, then the completion LV, the completion of with respect to this absolute value will be denoted as LV of L will be a local field. So like we have seen before that the completion of Q, completion of Q at this absolute value is QP is a local field.
There is
And
some
this is
doubt in
called-
this last statement. C. The K is local field if and only if K is complete and the residue field is finite. So from the previous fact B,
statement.
C statement, third statement, yeah. Second statement of the third statement.
Yeah.
If K is local field from the B statement, it is already complete. Right?
Yeah, that's one direction, right? So yeah.
And
so
then
this
why
is
this extra condition of residue field being finite?
Yeah, so then this will be needed to prove the reverse direction.
Okay.
So when K is local, that implies it is complete, and that will imply A modulo pi A will be finite. And when you assume that A modulo pi A is finite and K is complete, then you can go to the reverse direction and say that K is local. So this is an if and only if condition. And this is only one, this is only one direction.
Okay.
K complete does not imply that K will be local. So yeah, so as I said before, that K is complete, there may be higher dimensional local fields which are complete, but which are not local fields in the definition I have given. So that's why the residue field has to be finite.
Okay.
And we will need this linear algebra theorem to sketch a proof that all local fields are just the finite extensions of these things. So this is a theorem which the proof of which can be found here. I have given a reference.
Okay.
So which says that a locally compact topological vector space. So again, a topological vector space is just a vector space with a topology on it, and again the scalar multiplication map and the addition map are continuous with respect to the topology. So that topological vector space over a non-discrete topological field has finite dimension.
Did you define non-discrete topological field? Discuss.
Sorry?
What is non-discrete topological field?
Yeah, non-discrete means the topology on the field is not discrete topology.
Okay. Okay. Non-trivial.
The discrete topology means all the subsets are
open and closed.
So that is not the case. That will be just trivial, right?
Okay.
Yeah. So now using this, we can sketch a proof of that. That if L is a local field, then L is if L is Archimedean, then L is isomorphic to R or L is isomorphic to C. Otherwise, L is a finite extension of QP for some prime P or FQ T. This is the LoRa series with coefficients in FQ for some prime power Q. So we start with we just sketch the proof there are several small details that needs to be checked. So the proof is suppose that we have an non-trivial absolute value on K. So by fact B, K is complete, because we have assumed that L is local and there is a, sorry, this has to be L. So we have assumed that L is local and there is an absolute value. So by fact B, it is complete, right?
Mm.
So if characteristic of L 0, then we all know that L will contain a copy of Q, right? Because characteristic 0 field, the prime subfield is Q, right?
Mm.
Every characteristic 0 field contains a copy of Q.
Mm.
And also the completion of Q is contained inside L hat, which is equal to L because it is complete. So the completion with respect to any absolute value of Q is either by the theorem of Ostravsky is either QP or R, right?
Mm.
Because all the absolute values are either the usual absolute value or the periodic absolute value. So depending on that, there are only these choices that it is either QP or R. So L contains a copy of then L contains a copy of QP for some prime or R. And by this theorem, L is a vector space over these fields. And since these are locally compact, L is local field, that's why it is locally compact. So this is a locally compact topological vector space over these fields, which are also non-discrete topological fields. And that's why the extension as a vector space, this will be finite, QP or R. So what are the finite extensions of R? They are only R or C itself, right?
Yeah.
Yeah, so this case is done. Now when characteristic of L is P, then L contains a copy of FP. And again, then it contains a topological completion of FP. So it can be easily seen that any finite extension of a finite field cannot have a non-trivial absolute value. Since L has a non-trivial absolute value on it, L must contain some transcendental element over FP. And that's why L contains a copy of FPT. So this one can check very easily that why any finite extension of FP cannot have a non-trivial absolute value on it. And that's why there is some element T which is not algebraic over FP. And that's why L contains a copy of the field of fractions with this indeterminate or transcendental element T.
Mm.
And that's why L contains its completion also. And it is a theorem that any completion of these field of fractions, field of rational functions with coefficient in the prime subfield FP looks like the the field of Laura series with coefficients in some finite field. And again, by this theorem, by this proposition, it is a finite extension of the FQT. So these are the two cases proved. So is the proof clear?
Yes.
Yeah, so we have proved that all local fields are either R, C, or QP or finite extensions of QP, or FQ Laura series T, or finite extensions of FQ Laura series T.
Just one comment.
Yes, you.
I think you don't need to put Q and P is enough. If P Lorentz series T is enough,
Yeah,
as you complete T adequately and coefficients does not change.
yeah. Yeah, you are right. Okay, sure. Thank you. And here is one important lemma about local fields, and so which is known as the Hensel's lemma. This is one version. So there are maybe 3 or 4 versions of it, and all the proofs can be found here. So it says that if A is a complete discrete valuation ring, that is a ring which has a discrete valuation on it and which is also topologically complete with respect to the topology induced by this discrete valuation. So, and that has a unique maximal ideal M, and let K be the residue field. Then suppose that fx inside Ax is a monic polynomial whose reduction. Reduction means we are reducing the coefficients modulo this maximal ideal, and we get a polynomial inside this ring of polynomials with coefficients in the residue field. So if it has a simple root A bar inside the residue field, then A bar can be lifted to a root A inside this ring of A, F of F. So this is very important and has many applications, but I will not be able to sketch any applications of that.
Yeah, and your time is getting over, so maybe wrap up in 5-10 minutes.
Yeah. Now we want to study the extensions of local fields. So while studying extension, we need to see how the absolute value extends to the absolute value of on that extension. So here is an important theorem, which says that if we have an extra absolute value on a local field K defined by this formula, then it has a unique extension to a finite extension L, which is defined by this formula. The absolute value E of norm of L over Kx to the power 1 by the degree of the extension. And the valuation ring of L equals the ring of integers of L. And this formula also holds, which is the absolute value equals C to the power VQ of X divided by EQ, where EQ is the ramification index. So as I have said earlier, so if P is the unique maximal ideal of A, so here I have set the notation. So for all the following discussion, we are assuming that A is a complete discrete valuation ring. K is its field of fractions. L is a finite extension of K. B is its ring of integers. And we will refer to this as AKLB. So when we have that unique maximal ideal P of A, then P times B factors like this. This is the unique maximal ideal of P, and this is a power. So this is called the ramification index of the prime P. And we have that L over K is equal to EQ FQ. Thus,
What is
so
B,
L
Q,
over
B
K
over,
is,
what is this B over Q, A over P written simultaneously? Third line after the equation.
So this is the finite field extension. This is a
Okay.
finite field, and this is a finite field, and this is a
Yeah,
finite
yeah.
field extension.
Okay.
So FQ is the degree of this finite field extension.
And B is
And we
extension of A, or B A is extension of B?
Yeah, A is an A over P is an A over P is a finite field, and B over Q is a finite field.
And B and A are B is over A, or A is over B? It's global.
Yeah, B is over A.
Okay.
Yeah, so here we have its field of fractions K, then a finite extension, and then we have the ring of integers B of L. Yes, and we have this formula that the degree of extension is equal to EQ times FQ.
Mm.
So we say that L over K is ramified, is unramified when EQ is equals to 1. So this implies that the finite field extension is has the same degree as the local field extension.
So you are
So
this whole statement are in the local field condition environment, right?
yeah.
But these
Even
terms
if
make
it's,
sense in the global field arithmeticals.
No.
Inertia. No, ramification index, inertia degree. They
Yeah.
all have a valid meaning
They
there.
are all same. They are all same. But in case of global fields, there will be many prime ideals, not just one.
Okay. But definition
Many
is same.
means, yeah. The definition is same. And so here we see that unramified extensions of local fields correspond to finite extensions of this finite residue field of the same degree. So using this correspondence, one can show that every unramified extension of degree n of a local field K is actually isomorphic to K adjoint Z p to the power n minus 1. So that corresponds to this thing, that the extension of degree n of finite field is the splitting field of of this polynomial of degree p to the n, right? So using this fact, one can prove that any unramified extension of degree n of a local field K is isomorphic to K adjoint Z p to the power n minus 1.
It is some cyclotomic field.
Yeah, it is like a cyclotomic field.
Like or what?
And
It is
yeah, it is, but
generated
one
by
does not
some.
say it is a cyclotomic field because it's not the same as Q adjoint ZM.
Okay.
Because
Okay.
Q
So
adjoint ZM has degree phi m, but it is not of degree phi m. It is of
okay.
degree n. It
Hmm.
is of degree n, and its Galois group is isomorphic to Z mod NZ.
Okay.
That's why we don't call it a cyclotomic field. So there is more generally a categorical equivalence between this unramified finite unramified extensions of a local field and finite extensions of same degree of the residue field, which is given by this correspondence. So we are taking a finite unramified extension and sending it to the corresponding extension of the residue fields. So they will have same degree, and categorical equivalence means all the things will be functorial. So when we have the homomorphism from between two finite unramified extensions of K, if I look at the K algebra homomorphism, then though that set will be in bijection with the uh, corresponding the small K algebra homomorphism between these two finite fields. So this is the thing, and this says that for unramified extension of degree K, the Galois group is isomorphic to Z mod NZ. So this Galois group is extremely easier to study. And why we are concerned with the unramified extension is that every extension of a local field can be decomposed separately and studied as a part which is totally ramified and as a part which is unramified. This is unlike global fields. So for global field extension, we cannot decompose like this, but for local fields, we can do this. So, and if we take all the unramified, finite unramified extension and take the compositum, then we will get the maximal unramified extension of K. So this is an example that if QP is the local field, then the maximal unramified extension of QP will be a Galois extension, infinite Galois extension of QP, and the Galois group will be isomorphic to Z hat, which is the inverse limit of these cyclic groups. Z hat is known, Z hat is called topologically cyclic. Topologically cyclic means it has a subgroup which is cyclic and this dense. So this is a topological group, also known as a profinite group. And then I state this theorem, which actually states how an extension of a local field decomposes into two separate parts. So if you take a local field extension as AKLB, I have stated before. So, and suppose that the residue field extension is separable. So this will be the case always when we are studying local fields like finite extensions of QP, etc. So that will be always separable. So then there will be a sub-extension, intermediate sub-extension, such that E over K will be unramified and L over U will be totally ramified. By totally ramified, I mean that, by totally ramified, I mean that if Q is equal to 1.
How much is left
So
now?
when, sorry.
How much is left?
How much is left? Not much. Just a little.
Okay.
Yeah. So maybe it will be better to complete all the things. Just
complete.
And and the Galois group of U over K will be isomorphic to the Galois group of this finite extension, finite field extension, and the Galois group of L over E will be the isomorphic to the. This is called the inertia group. So when we have the decomposition group, and if I have and this is a theorem that there is a surjective group homomorphism from the decomposition group to the Galois group of L over K, and the kernel is known as the inertia group. So thus we have, and also the totally ramified part can be decomposed into totally tamely ramified and totally wildly ramified. So what is tamely ramified? So we say that it is tamely ramified when the characteristic of the residue field does not divide the ramification index. Tamely ramified case. And wildly ramified is defined to be when the characteristic of the residue field divides the ramification index. So there is another theorem which I haven't stated, but can be found in any advanced algebraic number theory books, which states that this totally ramified part can be decomposed into tamely ramified and wildly ramified. So this, so any local field extension is actually decomposed into this three parts. This is the unramified part. This is the totally ramified part, and this totally ramified part is separately decomposed into two parts. This is the totally tamely ramified, and this is the totally wildly ramified. So this this part has been studied well, but this wildly ramified part is very difficult to study in general. So that's why the name is also wildly ramified. Now we come to totally ramified extensions. So totally ramified extensions come from adjoining one nth roots of some uniformizer. So there is a theorem that if L over K is a totally ramified extension of a local field of degree n, then there is some uniformizer pi k of K such that L is isomorphic to K adjoint the nth root of that uniformizer pi k. So by using this theorem, we can get the maximal totally ramified, totally tamely ramified sub extension of K, which is denoted as KTM, which is the union of all these fields, K adjoint pi k to the 1 by n, where the union is running over all n greater than equal to 1, such that in GCD of n p equals to 1, because we are studying only tamely ramified cases. So the extension degree should not divide the characteristic of the local field, the characteristic of the finite residue field, which is P. So this says the union of all nth roots of unity of all uniformizers. So that's why it contains the total maximal unramified extension also, which is noted as KUNR. And it can be easily shown that this extension K tamely ramified over K unramified is generated by these uniformizers. And there is an isomorphism that the Galois group of these K tamely ramified over K unramified is isomorphic to the direct product of these p-adic integers or L-adic integers with L not equals to P. Because we are taking the inverse limit over all Z mod nz such that n and p has GCD1. So we are not taking the prime factor p. That's why this is isomorphic to the direct product of L-adic integers such that L is not equals to p. And now we can describe the Galois group of K tam over K, which is a theorem of Iyasawa. So let tau K be a topological generator of this Galois group, which comes from the generators of these cyclic groups Z mod nz such that GCD of n p equals to 1, because this is the inverse limit. So this is the inverse limit n such that GCD of np equals to 1 Z mod nz. So for Z hat, we have seen that the Z hat is defined to be the inverse limit of all Z mod nz, but here we are not taking those such that P divides it. And tau K be the generator of that group, and let Frobenius, this is known as the absolute Frobenius element. So let Fr be the generator of K U N R over K, which is isomorphic to Z hat. And we have this canonical short exact sequence. And since this map is surjective, we can take a pre-image of this Frobenius element here. And the very deep theorem of Iyasawa says that the Galois group of K Tm over K, that is the maximal totally tamely ramified extension of K, is topologically generated by this lift of the Frobenius element inside this Galois group. And there is a relation between this Frobenius element and the tau K. That is Frobenius K bar tau K times Frobenius K bar is equal to tau K to the power Q, where Q is the residue field extension degree. Sorry, the cardinality of the residue field of this K. So we get this big picture. So this is the final slide. So we have the total absolute Galois group of K, right? And we have decomposed these infinite extension into these parts. So first we have the maximal unramified extension, whose Galois group is Z hat. Then we have by Iyasawa's theorem that the totally tamely ramified extension is isomorphic to this the closure of this cyclic group generated by this lift of the Frobenius element. That is why it is said that it is topologically generated by this Frobenius element. Then we have that that maximal unramified extension and the totally tamely ramified extension has the Galois group direct product over the L-adic integers L not equals to K. And then we have this is known as the absolute inertia group, which is the inverse limit of all inertia groups of all finite sub extensions. So this is all we know very well. This part is not known very well. So for this, you can study the higher ramification groups. So there is a section in Neukirch's book called higher ramification groups. So
one question is that is this picture about the local fields
Yeah.
help to understand a particular similar picture about global field? Like if we say Q
No,
bar
no,
over Q and
no, no.
Galois is the main
That's
absolute
why
Galois group.
no. That's why we like to study QP bar over QP,
Okay,
which
but
is a
QP,
which is a subgroup of the absolute Galois group of Q.
so this
This is a
QP bar is
subgroup.
equal to QP is particular example of this that figure, right?
Yeah. You can take
So,
QP, A to be
so,
QP.
so understanding this picture would certainly help in this bigger right hand global Galois group, right?
Yeah.
How
So
much
if
it
we
is? Any
yeah,
important theorem? Any important theorem has been derived in studying this subgroup of Galois group?
yeah, of course. So when we study Galois representations, so we mainly study the Galois representations of these subgroups.
And
So
conclude about
studying
the
Galois
bigger.
representations of this group is very difficult. So there are
Okay.
local cohomology and global cohomology. So first we define local conditions and then we define global conditions. So there are
Is
many
how much
theorems.
how much big is this subgroup inside the bigger group?
Yeah, so we don't exactly know these things. So we
Okay.
cannot measure these things, right?
Index wise or something, no?
Yeah. In fact, we don't try to study any internal property of these groups. Only we want to study how it interacts with other with vector spaces or geometric objects, etc.
Okay, okay.
That's right. And
Okay.
interest for local fields is that it decomposes like this, and the parts of the Galois groups are easily understandable than the global extension. So we don't have a very nice picture for this.
Okay. And one more, okay, we will keep discussing. Probably your second talk will start from
Yeah,
somewhere here only, right? So
yeah,
you will be introducing the Galois representation, discussing the representation
yeah.
of local Galois group or global.
Yeah, so I will study both.
Okay, great. Thanks.
So in theory, there are much study of these local Galois groups. So there is a separate book on only periodic Galois representations.
Okay, okay.
Sorry. Sorry.
Sorry, just as a comment, I want to say that the local Galois groups cover the global Galois group. All the local Galois groups together covered, but in some sense they are more little than the global Galois group. They are because they are solvable. The local Galois groups are solvable as a result in higher ramification groups, but the global Galois group is from being solvable.
So the Galois group of Q is much more complicated than this, but
but
we can,
as you said, one of the best ways of study global Galois group is the local counterparts and patching data.
Yeah.
Okay.
Yeah, so that's what you will be also talking about, right? On deformations of Galois representations.
Yeah, sure.
Yeah.
Thanks for the wonderful presentation. And if anyone has any other questions, if not, let us thank the speaker. And we will meet next Saturday again. Thanks, Subra. I'm ending the meeting.
Thank you, Shubhra, for nice talk.
Yeah, sure.